So we've been talking a lot about how to normalize our data. Now it's going to come as some surprise to you. We're going to talk about how to denormalize your data. So there's always this conflict between normalizing fully and only normalizing partially. What I need you to know and understand is that the best approach is to know how to normalize your data fully. And then, if you need to for performance reasons, back off that normalization a bit. But in this way, rather than being accidentally denormalized, you're being intentionally denormalized. So we're going to talk about what it means to denormalize, and we're going to talk about materialized views, which is an attempt to be normalized and denormalized at the same time. So stay tuned. In a fully normalized database, you eliminate duplication, you eliminate redundancy, but you do increase the number of joins that are required in order to reassemble your data. Denormalizing is done primarily because the join operation is an expensive one, and the more we're joining, the more our queries take a performance hit. So here are 4 denormalization strategies we will discuss: how to denormalize derived values, keeping details with the master, keeping one detail with the master, and adding short circuit keys. The first technique is to denormalize derived values. When would you do this? You would do this in circumstances where you frequently need those derived values and when you're not changing data frequently. Here's an example. Look at our customer table. It has the first name, last name, the street, the zip code, the phone number, and the email, which is great. It does not have the city or state. That's because the city and state can be derived from the zip code. So fully normalized relational database techniques would tell you to build the customer table and then build the zip codes table. And you can look up the city and the state from the zip code, but that's a lot of looking up. And the zip codes aren't going to change that often. So maybe it's a good idea to take the city and the state columns and add them to the customer table. Now we'll have data redundancy, and we'll have to make sure that we have the correct information, but this is a pretty safe denormalization. Here's another example of denormalizing derived values. We have a product table that we might be selling, different information about the products, like these different fans. And then we may have a different table, a normalized table, with the different ratings from all of the users. Now, when we show the products on our website, we want to show the average rating. Now, we can do this in a couple of ways. We can obviously join the tables and do some aggregation. We can make a view that will also do the same thing and give us the average rating. But a view is nothing more than a saved query. And so all the impact of joining and recalculating every time is going to be present. So we frequently need derivable values. In this case, though, we are altering the data frequently, so it's a little more risky denormalization. But to denormalize this, we might have an average rating column for the product table, which you can see in red. And that's going to be the result of the average of all the individual ratings. Now, the problem is that this rating information gets stale very quickly and may have to be regenerated. And we are duplicating something we could have derived, but we're also saving time when we query the product table. We may have to put some controls in place to make sure that the rating stays updated. But again, we have denormalized, we've duplicated data, but we've made retrieval of that average rating a little bit easier. It no longer has to be calculated every time we run a query. So to summarize the pros and cons of denormalizing derived data, the pros are that you don't have to look up these values every time you need them. They're right there in the table, makes querying very quickly. And if there are any calculations you need to perform, such as the average rating, you don't have to perform them every single time we run a query. But the disadvantages are also pretty strong. Now, whenever we add a new rating or we change some information, we have to recalculate this derived data. So we have to have code running that's going to keep our database in sync because we've duplicated data. And because of that data duplication, if we're not careful, we can lead to data inconsistencies. Here's another example. It's called keeping details with the master. Normally, when we talk about a master record, that's like the parent record, and then the details would be all the children associated with that record. So for example, in this case, we have a list of instructors. We'll call the instructors the master record. And then through normalization, as you can see in these three blue tables, we will take the instructor ID, we will link them to all the different courses they teach in the bridging table, and then the course ID will translate into the course name. This is perfectly normalized data, but the way to denormalize this would be to add in that red column on the instructor table. So for example, we could look at instructor 14, James Wilson, see that instructor 14 has taught two different courses in the bridging table, and those two courses correspond to Organic Chemistry 1 and Organic Chemistry 2. That's how you would work in a normalized system. But in a denormalized system, I might have this field called Courses Taught, and I could put in there the two courses that James Wilson has taught. This technique will work well if you have a small number of detail records for each master, as we do in this example. And you notice that we're violating the comma rule. This is certainly not in first normal form, but the idea is that when I retrieve instructor James Wilson, I know exactly what he is teaching. And similarly, the other instructors also have this courses taught column added. It breaks normalization, and we're going to have to be very careful, because if we add in something new into this table for James, say we add in inorganic chemistry as another course that James Wilson can teach, in a relational database system, we just add the row into the bridging table. But in a denormalized system, we're going to have to go back up to the courses taught, and we're going to have to make a change there. We're going to have to make sure that we add in an additional course right here. So when you do this type of denormalization technique, keeping your denormalized column correct is a challenge that you'll have to do with database programming. There's a variation on this theme where you can keep only one detail with the master. So consider here we have customers from Ann Haim down to Derek Wilson, and we have an order table that shows what orders they've placed with us in the past few weeks. One thing we can do is we can add another column to the customer table for their last order. Notice that this last order column has values from the order table, the order number, the order date, and the amount of the order, but it only has one detail record for every master. Again, the customer is master and the orders are details. But it has the last order. And we can do this through concatenation. And it's really nice because now I have one record for each customer to show their very last order. I don't have to reach into the order table and find the most recent order date. It's right there in the customer table. So I've denormalized, but then again, I have to keep this current. Every time someone makes a new order, not only do I have to add that to the order table, but I have to duplicate the new order information back up in the customer table. Our last technique is called the short circuit keys. Let's take a look at the top part of the slide, the normalized part. Notice that we have a section object in the middle, and the section object has a key for the instructor, and it has a key for the course that's being taught. And each course is affiliated with a particular department, and it maintains a department ID. So if I wanted to show information about the section, I would use the instructor key to grab the instructor. I would use the course ID to grab the course, and then I would do a join from course to department to get the department name, who was sponsoring the course. That's a lot of joins. How can we denormalize this? You can denormalize this as you see below, where we have added a department ID into the section table, and we've added a new relationship directly to the department table. Now this is problematic because why? I can get the department two different ways, directly from section or through the course, and those two different ways could contradict each other. This level of short-circuiting is really only helpful if I can cut out the middleman table. So if I had queries that relied on the instructor, the section, and the department, and sort of cut out the course table, then that short-circuiting relationship will help me get that without adding in course into the join. However, if I do need to have all four tables, this denormalization doesn't really help much. Here are a few great tips for denormalization. The first is, as I've said before, always normalize your database fully, and then instead of trying to denormalize the entire database, focus on the particular parts that you want to speed up. If something is slow, focus on denormalizing that aspect of the system. Understand your application really well and know what parts of your system are going to be affected by denormalization. Also, analyze how often data is changing in your application. If data is changing too often, maintaining integrity could become a problem. But if data is not changing very often, then you could be okay. And take a close look at what parts of the application are having performance issues. Sometimes you can fine-tune your queries. Maybe your queries are inefficient rather than denormalizing the database. And learn about different data storage techniques. Picking the most relevant one can help you do without denormalization. Denormalization again can speed up some of your queries, but it's not without its drawbacks. You're going to have lots more storage space because you're duplicating data. You better be very careful and document every time you've denormalized, because if your database changes, you may have to change all of these rules and all this code. And the fact that you have all this duplication means you have lots of chances for data anomalies to occur. That's going to require you to have more code, and you have to take care of every single case of duplicate data. And you're going to have to use triggers, stored procedures, and transactions to avoid data anomalies. It's going to be very easy for you to do something and not complete all the actions that are needed, and your database is out of sync. And while you may have sped up your queries, you might have slower operations. Your updates, your inserts, your deletes could be slower. So if you're going to be doing an awful lot of write operations to the database, this may actually be slower than a fully normalized database. So what do we do with this? Do we normalize or do we denormalize? And in an upcoming video, we'll talk about one technique to have it both ways, have normalization and denormalization through a construct called materialized views. I hope you check out that video and learn more about that very important and emerging technique.